Welcome back. In our last video, we used a clever whittling trick to build the rule for 11. Chop off the very last digit of your number, subtract it from the entire remaining front section, and check if it's divisible by 11. But I promised you a fun secret. There's another incredibly elegant rule for 11 that does not require chopping numbers at all. It is beautifully similar to how we just add up the digits to test for 3 and 9, but with a fascinating rhythmic twist. Here is the secret rule for 11. You simply alternate adding and subtracting the digits. Does it matter if you start from the left or the right? Actually, it really does not matter. If you calculate the sum from left to right, and your friend does it from right to left, your final totals might have opposite signs. One might get positive 11, and the other negative 11. But since both are perfect multiples of 11, you will both arrive at the exact same mathematically correct answer. Let's see this rhythm in action. Example 1. Let's test the number 2,728. Moving left to right, we alternate signs. 2 minus 7 plus 2 minus 8 equals negative 11. Since negative 11 is obviously a multiple of 11, 2,728 is in the club. Example 2. Let's try 1,364. Again, alternating left to right. 1 minus 3 plus 6 minus 4 equals 0. Remember, 0 is a perfect multiple of 11. Because 11 times 0 is 0, because our result is 0, 1,364 is absolutely divisible by 11. Why does this add, subtract, dance magically detect multiples of 11? The secret lies in a beautiful mathematical pattern regarding the powers of 10. Before we get into the heavy algebra, let's just look at the numbers and build some intuition. Let's look at the powers of 10 and how close they sit to the 11 times tables. 10 to the power of 0 is 1. 10 to the first power is 10. That is exactly one step below 11. 10 to the second power is 100. We know that 99 is a multiple of 11, which means 100 is exactly one step above a clean multiple of 11. 10 to the third power is 1000. It turns out that 1001 is perfectly divisible by 11, which means 1000 is exactly one step below a multiple of 11. Do you see the beautiful pattern emerging? Every single power of 10 ping-pongs back and forth. It is always exactly one step above, or exactly one step below, a clean multiple of 11. We can define this pattern with two simple statements. For any power k, if k is even, 10 to the power of k equals 11p plus 1. If k is odd, 10 to the power of k equals 11p minus 1. Note that in these equations, p just represents some integer, meaning 11p is a perfect massive multiple of 11. Let us prove that this pattern is absolutely true using two powerful mathematical tools, the binomial theorem and mathematical induction. To prove this elegantly, we can use the binomial theorem, which tells us exactly how to expand algebraic expressions raised to a power. Instead of writing 10 to the power of k, let us rewrite our base of 10 as 11 minus 1. So our expression becomes open parenthesis 11 minus 1, close parenthesis raised to the power of k. When we use the binomial theorem to expand those brackets, it generates a long string of terms. The first term contains 11 to the power of k. The next term contains 11 to the power of k minus 1, and it descends step by step. But here is the beautiful part. Every single term in that massive expansion is multiplied by at least 111, except for the very last term. Because almost every term contains an 11, we can group all of them together, factor the 11 completely out to the front, and package that giant chunk as 11p. What is that one single isolated term left at the very end of the expansion? According to the theorem, it is simply our second number, negative 1, raised to the power of k. So, our entire massive binomial expansion simplifies perfectly down to this. 10 to the power of k equals 11p plus negative 1 to the power of k. And here is where the even and odd magic perfectly emerges. If k is an even number, taking negative 1 to an even power cancels out the negative, leaving a positive 1. The equation becomes 10 to the power of k equals 11p plus 1. If k is an odd number, taking negative 1 to an odd power stays negative 1. The equation perfectly becomes 10 to the power of k equals 11p minus 1. With one algebraic stroke, we prove both sides of the pattern. If we want to prove this works into infinity, we use induction, the mathematical domino effect. Let's test the base cases. Let's test k equals 0, which is an even number. 10 to the power of 0 is 1. Does 1 equal 11 times 0 plus 1? Yes? The first even domino falls. Let's test k equals 1, which is an odd number. 10 to the power of 1 is 10. Does 10 equal 11 times 1 minus 1? Yes. The first odd domino falls. Now for the inductive step. Let us assume our rule is true for some random power k. We must prove it forces the next power, k plus 1, to follow the opposite rule. To find the next power of 10, we just multiply the current one by 10. 10 to the power of k plus 1 equals 10 times 10 to the power of k. Scenario A. If the current k is even, we substitute our even rule, 11p plus 1, into the equation. 10 times the quantity 11p plus 1 equals 110p plus 10. Here is the clever trick. We rewrite 10 as 11 minus 1. 110p plus 11 minus 1. Factor out the 11 from the first two pieces, and you get 11 times the quantity 10p plus 1 minus 1. Look at that. We have a new multiple of 11 minus 1. We just perfectly generated the rule for an odd power. Scenario B, if the current k is odd, we substitute our odd rule 11p minus 1 into the equation. 10 times the quantity 11p minus 1 equals 110p minus 10. We rewrite negative 10 as negative 11 plus 1. 110p minus 11 plus 1. Factor out the 11, and you get 11 times the quantity 10p minus 1 plus 1. Boom, a new multiple of 11 plus 1. We perfectly generated the rule for an even power. The dominoes will alternate falling, perfectly swapping between plus 1 and minus 1 for all of infinity. Now, let's bring back our generic base 10 number. Any number is just a massive addition problem built from its digits, scaling up by powers of 10. The number equals d0 plus 10 to the first power times d1 plus 10 to the second power times d2 plus 10 to the third power times d3, and so on. Let us swap out every single power of 10 using the alternating even and odd rules we just proved. 10 to the 0, an even power becomes 11p0 plus 1. 10 to the first power, an odd power, becomes 11p1 minus 1. 10 to the second power, an even power, becomes 11p2 plus 1. 10 to the third power, an odd power, becomes 11p3 minus 1. When we substitute these into our giant number equation, we distribute the digits into the parentheses. The number equals 11p0, d0 plus d0, plus 11p1 d1 minus d1, plus 11p2 d2 plus d2, plus 11p3 d3 minus d3, going all the way up. It is time to rearrange the furniture. We gather every single piece that is attached to a multiple of 11, drag them all to the front, and factor the 11 out completely. We will call this giant chunk Part A. Part A equals 11 times the quantity p0 d0 plus p1 d1 plus p2 d2, and so on. What is left over on the right side? We look at our isolated digits, and here is what remains for Part B. Part B equals d0 minus d1 plus d2 minus d3, and so on. We successfully transformed our original number because that giant front chunk, Part A, is mathematically guaranteed to be divisible by 11. The divisibility of the entire number rests solely on that tiny leftover alternating sum, Part B. But wait a second. Look closely at that leftover piece, positive d0 minus d1 plus d2. This formula tells us to start from the right side, the unit digit with a plus sign. But at the beginning of this video, I told you to start from the left side with a plus. Did we make a mistake? Let's figure out what the sign of that leftmost digit is actually supposed to be. If our number has an odd amount of digits, like a 3-digit number, our leftmost digit is d2. In our formula, d2 is positive. So if the number has an odd length, starting from the left with a plus perfectly matches the exact math. But what if our number has an even amount of digits, like a 4-digit number? Our leftmost digit is d3, and in our formula, d3 is negative. The strict math says that for even length numbers, we should actually start from the left with a minus. So why does starting from the leftmost digit as a plus still work every single time, even for those even length numbers? Bring back our favorite mathematical rule. If 11 perfectly divides a number, it perfectly divides its exact opposite. If you take a formula that is logically supposed to start with a minus, but you intentionally start it with a plus, all you are doing is flipping every single sign in the entire equation. You are just calculating the exact opposite of Part B. If the true mathematical formula resulted in positive 11, your flipped version will give you negative 11. If the true answer was negative 22, you will get positive 22. And if the true answer was 0, well, the opposite of 0 is just 0. Because both sides of the 0 line belong to the 11 club, the starting sign literally does not matter. You do not need to pause and count whether your number has an even or odd amount of digits first. You can just start from the left side with a plus, confidently alternate your signs, and know that the math will safely guide you to the truth. No magic, just the beautiful rhythmic power of algebra. If you enjoyed uncovering the hidden gears turning inside our math system today, make sure to hit that subscribe button. It really helps the channel grow, and it guarantees you won't miss our next deep dive into the secrets of mathematics. See you in the next one.